great pleasure to introduce our colloquium speaker for this week, Phiala Shanahan. So Phiala is a member of the faculty at MIT, and today we're going to hear from her about from quarks to nuclei, the building blocks of the universe. Phiala has been working in lattice QCD since her PhD. Maybe just a couple of highlights. So she has received the Kenneth Wilson Award for Excellence in Lattice Gauge Theory in 2020. And I see that even more recently in 2021, she was awarded the APS's Maria Goldberg-Mayer Award for Excellence in Physics. So Phiala is really a leading light, I would say, in the lattice community and a great communicator. And most impressively as well, has also just recovered, I hope, from hosting the largest ever lattice conference, which was held virtually by MIT this year, 2021, and featured, I think, over 900 participants. So it was a truly astonishing experience and really a tour de force in organization. So just getting that conference photo alone was absolutely astonishing. So Phiala, it's really a great pleasure to welcome you, and I'm really happy that you were able to accept the invitation. I know that you have to run quite promptly after your talk, but hopefully there'll still be time for some questions for what I'm sure will be a really interesting colloquium. So I'll hand over to you. Thank you.
Thank you very much for the lovely introduction, and it's a pleasure to be here virtually. I hope one day to visit in person. Okay, so the topic of this talk is really the structure of matter. And of course, we know that matter is composed of atoms, and atoms have a densely packed nuclear core of protons and neutrons orbited by a cloud of electrons. And our modern understanding is that the structure of matter goes one layer deeper still. And so the protons and neutrons inside the atomic nucleus themselves have substructure. So they're made of matter particles called quarks, held bound or glued tightly together by the strong nuclear force manifesting as force-carrying particles known as gluons. And so to the best of our current understanding, the quarks and the gluons are it. They're fundamental particles. They can't be divided any further. And of course, it would be very exciting if one day we find out that that's not in fact true. So the quarks and the gluons and their interactions are encoded in what's known as the standard model of elementary particles. And so the framework was put together in the 1970s. It contains just 17 fundamental particles. You can see them here on the slide. We have matter particles, the quarks, we have leptrons like the electron and the electron neutrino and heavier cousins, and we have force-carrying gauge bosons for 3 of the 4 fundamental forces, so notably excluding gravity, put together in this very elegant, very beautiful, very predictive framework. And in fact, a number of the particles of the standard model were predicted from the symmetries of the theory before they were seen experimentally. So most recently, if we go back to some of those that some of us might remember, so the W and Z bosons were in 1983, the top quark in 1995, the tau neutrino in 2000, and then most recently, of course, the Higgs boson in 2012 was the last remaining piece of this puzzle. And so this is really an extraordinarily successful description of the matter in our universe. It's the best physics theory we've ever had. It's withstood almost every experimental test. And to give just one example of the really extraordinary success of the standard model, we see here the anomalous magnetic moment of the electron. So that's how much torque an electron feels in a magnetic field. And the anomalous is just the difference here from the tree level or from the classical result, that is G equals 2. So you might have heard a bit about this quantity, G minus 2 for the muon in the press in the last few months, where there's an interesting tension between predictions and experimental measurements. But here for the electron, this is the most accurately verified prediction in the history of physics. I don't know if there are students here taking quantum field theory classes, but if there are, you'll understand when I say the heroic effort this takes to make this theory prediction. Up to 5 loops of Feynman diagrams, that's 12,000 Feynman diagrams more or less, and 30 years of effort to make this prediction from theory for this quantity that compares beautifully with experiment to 12 significant figures. And it's not just sort of static quantities where the standard model is beautifully predictive and describes what we observe about the universe, but it's predictive over a very wide range of scales. So what we see here is deep and elastic scattering of an electron on a proton. So fire an electron at a proton so hard that it hits and it breaks the proton apart. And we describe that scattering through quantities called structure functions, which are shown here on this figure. And on the horizontal axis, we have energy. You see a log scale, so ranging over many orders of magnitude here. And you have the theory predictions in the bands here, and you have the experimental measurements in color, and you see this beautiful agreement between theory and experiment over all of these many orders of magnitude of energy scales. Okay, so beautifully predictive, successful theory. However, we also know that it doesn't describe everything that we observe about the universe. So just one example that I'll come back to later in the talk. Of course, nothing in the standard model can describe dark matter, which in fact we know dark matter and dark energy between them make up most of the energy density of the universe, and the matter actually described by the standard model is only this 5% sliver of the energy density pie. So dark matter is matter, but it's not standard model matter. We don't know what it is. Dark energy is whatever is responsible for the accelerating expansion of the universe. And so none of this is described by our standard model theory. That's not all. So dark matter and dark energy are just one example. Neutrinos have mass. We see them oscillate, which again, if there are students in the audience, just a simple quantum mechanics two-state system problem can give you this intuition that the mass eigenstate doesn't match the flavor eigenstate of the neutrinos. So you see them oscillate between different types of flavor as they propagate, which tells us that they have mass, which they don't in the simplest version of the standard model. There's a matter-antimatter asymmetry that we don't understand. So the standard model treats matter and antimatter almost the same. There's a little bit of a difference, but not enough to explain why galaxies and so on are all dominated by matter, not antimatter. If the Big Bang created approximately equal amounts, approximately everything should annihilate. Gravity is not included. There are naturalness problems. Why is there such a discrepancy between the weak and the gravitational scales? So lots of evidence for physics beyond what's described by our beautiful theory. So we, of course, make huge efforts as a physics community to search for and to constrain physics beyond what's described by the standard model. And there are many ways of searching for new physics. Just one that I'll focus on through this talk is through experiments at what we call the intensity frontier. So that's where we have experiments with the sensitivity to really probe the rarest standard model interactions and look for deviations from our theory predictions. So this includes experiments like dark matter direct detection experiments, neutrino physics experiments, and so on. And what these types of so-called intensity frontier experiments have in common is that they use nuclear targets, which if you're looking for something very, very rare, makes a lot of sense. If you're looking for something rare, you want to increase the chances of seeing it. You want to increase your cross-section as much as possible. So you want to build a very large detector. Say for a dark matter direct detection experiment, you're looking for dark matter to hit your detector. So you build the biggest detector you can, which of course means assembling what we can assemble en masse here on Earth, which is nuclei as your detector. And so all of these intensity frontier experiments use nuclear targets. And so to disentangle the new physics from the standard model physics, we really have to understand the standard model physics of the protons, the neutrons, and the nuclei in those targets, in those experiments. So this brings me back to this question of understanding the structure of matter from the standard model. So understanding protons, neutrons, nuclei from this fundamental theory, which is important really for these two main reasons. Firstly, for its own sake, we have this beautiful theory. We'd like to see how all of the complexity of nuclear physics, all of the complexity of matter emerges from just those 17 fundamental particles. Can we see how we go from quarks to protons to nuclei, eventually to atoms to chemistry? How does it all come out of this theory? But then secondly, we need to understand it in order to constrain the physics beyond the standard model for the backgrounds and for the benchmarks in our searches for new physics. So that's the motivation for this sort of study of the structure of matter from the standard model. And it's also really the outline of this talk. So after a little bit more introduction, we'll talk about just a couple of examples for both 1 and 2 here as the main motivations. And then at the end, I'll come back for just a few minutes to give you a hint of how advances in computing and algorithms feed back in and let us learn more about the structure of matter. Okay, so to talk about first principle standard model calculations is to talk about the strong force. That's quantum chromodynamics. It's part of the standard model. And the strong force is the strongest of the four forces in nature. It's responsible for binding the quarks and gluons together into protons and neutrons, for binding the protons and neutrons together into nuclei. So of course it's relevant when we're asking questions about the structure of protons and neutrons and nuclei, which we want to understand from the standard model. But this theory, the strong force part of the standard model, is particularly challenging to study because it's non-perturbative at low energy scales. And so why low energy scales? Well, those are the energy scales relevant to something like the structure of a nucleus at rest in a detector, right? And so what this means is that the coupling here of the theory becomes large at low energy scales. So on the horizontal axis of the plot, we have energy moving to the left, energy is becoming small, the coupling here becomes large. Now, if we're over here where the coupling is small, we can expand in powers of that coupling. Take a small number and you square it and it's smaller still, cube it, it becomes smaller again. So you can do a perturbative expansion. If you want an answer to some precision, you can expand to the relevant order and stop. But when the coupling is large, you can't do that. So we can't use this sort of a perturbative approach. And what we're left with is the only known way to study the strong interactions in a systematically improvable way through what's called lattice field theory or lattice QCD, where the idea is that the equations of QCD, which ultimately calculating something in QCD looks like taking integrals over the values of the quark and gluon fields, becomes discretized onto a space-time grid or lattice in such a way that you can do the calculations numerically. So it's basically a numerical approach to QCD in this non-perturbative region. So what you want to imagine a calculation looking like is very, very high dimensional integrals in something like 10 to the 9 to 10 to the 12 variables for state-of-the-art calculations. So doing those integrals is a massive computational challenge. Of course, doing a numerical integral in such high dimensions, you have to do something smart to be able to even evaluate it. So what we do is we use important sampling, and the intuition you can have just thinking about quantum mechanics here is in quantum mechanics, we know that the paths near the classical action dominate and others are less important. And so you can think about what we do as sampling those important paths, or which translates into important field configurations, correspondingly more, and the less important ones correspondingly less, with the right weightings, so that you can do this integral very efficiently, rather than sampling the contributions that are very small, rather than sampling them a lot. We sample the important ones more. Okay, so something I want to emphasize about this approach is that it really is systematically improvable, and it has the same free parameters as the theory of QCD itself. So that's the masses of the quarks, of our fundamental particles, and the strong coupling. And so once you fix those by matching to some number of experimentally measured things, so masses of some particles, for example, to fix the quark masses, and you have one additional experimental input to fix the strong coupling, or equivalently the lattice spacing in some physical units, then everything else you get out of the calculations, from details of the structure of the proton all the way up to aspects of nuclear physics, are predictions of the theory itself. So importantly, when we want to go and talk about nuclear physics, it's important to note that there are no proton or neutron degrees of freedom in these calculations at all. The quarks and gluons in the standard model are the degrees of freedom. So there's no sense in which we are modeling a nucleus as a collection of protons and neutrons. In fact, all of that structure comes out of the dynamics of QCD and the quarks and gluons from the ground up. And then we have systematically improvable predictions. So in the limit that the lattice spacing becomes small, the volume becomes large, you can show that you can recover the continuum results that you're looking for. Okay, so these calculations are extraordinarily computationally expensive. So they use many millions of CPU and GPU hours to give some sense of scale. The laptop that I'm using to give this talk would need about 30 to 50,000 years to do some of the calculations that I'll show results of. Of course, we don't use laptops, we use big computers. So this one here is Summit. It's the largest in the US. And for a sense of scale, if every person on Earth did one floating point operation every second for a year, that's about what Summit can do in a couple of seconds. So really large scale computing. This computer is now surpassed by Fugaku in Japan, but we're still talking about months of running on the largest supercomputers in the world. So nevertheless, extreme computational challenges in doing these very high dimensional integrals, but the approach works. And I really don't have time to give a review at all. But what I want to emphasize is that in the last 5 or 6 years, we've reached a real precision era of using this sort of a tool, lattice QCD, for single hadron properties. And so now there's a deep complementarity between theory and experiment. So just as a few examples, here we have the proton-neutron mass splitting here, the difference between the proton mass and the neutron mass, which you can see in the theory calculation really emerge as a delicate cancellation between the strong interactions pushing it one way and electromagnetic interactions pushing it the other way to give you this delicate cancellation and the exact result that you agrees with what you measure in nature. And the other points on this plot are just different splittings between different members of what we call barrier and isospin multiplets, so different pairs like the proton and neutron. And for some of these, in fact, the theory predictions are more precise than the corresponding experimental result. Many of the basic thermodynamic properties of high temperature QCD, including calculations of things like the crossover temperature or the equation of state, quark number susceptibilities have been calculated. And essentially important insight for understanding the properties of the quark gluon plasma that you get in heavy ion collisions have been calculated using these tools. There's been lots of excitement in the last months that lattice QCD might play a key role in better understanding the current tensions in muon G-2. So we talked about electron G-2, the most accurately verified prediction in the history of physics. For the same quantity for the muon, there's an interesting tension between theory and experimental results that we see here, and lattice might play a key role in understanding that. And then finally, in contrast to the precision era of lattice QCD for single hadrons, we're just, as we'll see through this talk, at the very beginnings of a new era of understanding not just single hadrons, but also nuclei, nuclear structure, reactions from the standard model through these tools. So what we see here, this is the NP to D gamma transition. So that's the first nuclear reaction that happened in the seconds and minutes after the Big Bang. It's the first step of Big Bang nucleosynthesis pathway. And from the standard model, it's been calculated here on the horizontal axis is the pion mass squared. Of course, in nature, the pion mass has one specific value. The calculations can't quite be done at that value yet for reasons of computational cost, but you can see an extrapolation from larger values down to the physical point. And it's really this progress in nuclear physics at the edges of being able to do these same sorts of controlled first principles calculations that I want to focus on today. Okay, so to emphasize the point, in this era of precision and control and the beginnings of precision and control for nuclear physics, theory and experiment are really beautifully complementary, and we'll see a few more examples of that through this talk. Let's talk a little about what we can learn about the emergence of the complex structure in nature from first principles standard model calculations. And I want to draw your attention in particular to what theory calculations can tell us about the role of gluons in protons, neutrons, and nuclei. So gluons being the force carriers of the strong force, we of course know that they're important in the structure of the proton or a nucleus. They're responsible for binding the quarks together into the proton. But actually in comparison to what we've learned about the quark structure of in particular the proton or the nucleon over the last 60 years, we know very, very little about the gluon structure of the proton. And the reason is that it's much more difficult to access experimentally. The gluon doesn't couple to an electromagnetic probe. So lots of the experiments that we've done to learn about the internal structure of the proton in terms of its quarks don't tell us as much about its gluon structure. So there are still fundamental qualitative questions that we don't have any answers to at all. So when I say aspects of the gluon structure of the proton, what do I mean? Well, everything from the most simple static properties you can think about. Things like, how much do gluons contribute to the proton's mass, or to its momentum, or to its spin compared to the quarks? Up to questions about the three-dimensional structure of the proton. What's the three-dimensional distribution of the gluons compared to the quarks? That's encoded in things like gluon distribution functions and form factors, and we'll come back to in a minute the pressure distribution generated by the gluons inside the proton. And then we can go up to nuclear physics questions, which I won't have time to get to in this talk, but I'm happy to answer questions about, which is, well, how is the gluon structure of a nucleus different from the gluon structure of the protons and neutrons? We know that a pretty good model of a nucleus is there's a bunch of protons and neutrons stuck together, but we also know that fundamentally the structure is actually coming from the quarks and gluons of QCD. So how are the gluons playing a role explicitly in a nucleus structure as different from proton structure? So all of these questions we can think about answering from theory calculations. And in particular, it's an exciting time right now to try to do this, to try to do the first principles QCD calculations of some of these aspects of the gluon structure of protons and nuclei, because we have an expectation that within the next decade or two, we might actually have first experimental measurements too. So part of that excitement and expectation comes from the electron-ion collider. So it's a new collider to be built in the US, where funding's recently been approved. Site selection just happened last year. And so this is now something on the time scale of a decade, 15 years, where we might expect to actually have measurements of some of those fundamental questions about the gluon structure of the proton for the first time. Okay, so let's think about one of the very simplest things we can ask. So how's the momentum of the proton decomposed into its different components? How do the quarks and gluons inside the proton carry its momentum between them? So this is one of those simple quantities that's a single hadron, asking about single hadron structure, where, as I mentioned before, lattice QCD calculations now have fully controlled systematic uncertainties, in many cases competitive with or better than experiment. And in particular, something you can do fairly straightforwardly in a theory calculation that's much harder experimentally is to separate out all of the different contributions to the momentum, one by one by one. And that's what you're seeing here in this figure. So this is saying that up quarks contribute about 36% to the momentum of the proton. Down quarks, about 19%. Strange quarks, charm quarks. Gluons, about 43%. And you can add all of them up and you get, in fact, 100%, as you should, from all of the pieces coming together. So we're now really in an era, and it's just the last few years, of these sorts of precision calculations of these simple questions about the gluon structure of the proton. But then we can go a little further. To go beyond these sort of most simple static quantities and thinking about the QCD structure of the proton, one other thing we can ask about, which is in some sense a very intuitive question, is how the quarks and gluons contribute to the pressure distribution inside a proton. So what's here on the slide is a cartoon. On the horizontal axis, we have the radial distance out from the center of the proton. So here's the center of the proton. We're moving out along a radial direction. Here we have that radial distance squared times the pressure distribution. So I'm plotting this particular quantity because this is the thing that has to integrate to zero for stability. So if there's a peak, if there's a repulsive pressure, there also has to be a trough, a confining pressure or a compressive force there. So looking at just the cartoon, we can ask a lot of questions. We can say, well, what's the peak pressure in a proton? Does our intuition tell us it should be more like the pressure in a bike tire or more like the pressure in a neutron star? 10 to the 5 Pascal versus 10 to the 34 Pascal. How do quarks and gluons contribute? Do they have similar contributions to make up this pressure distribution? Do they have very different contributions? What's the radial extent of the pressure distribution? Is it similar to what we usually think of as the proton radius, where when we think about the proton radius, you're thinking about the charge radius? That's the radius as seen by an electromagnetic probe. What if we really think about it sort of quark and gluon density radius as manifested in something like the pressure distribution? So these are all questions that we can start to ask. And so recently we were actually able to calculate the individual quark and gluon pieces of the proton's pressure distribution for the first time from lattice QCD to begin to answer some of these questions. So the quark contributions were measured experimentally in 2018 in this work here in an experiment at Jefferson Lab. But the gluon parts had never been determined before. So what we have is a really nice example of the complementarity between theory and experiment. We were able to take the experimental measurements of the quark parts, theory calculations of the gluon parts, so neither theory nor experiment has both, put them together to get the first complete picture of the proton's pressure distribution. And in fact, that's what you're seeing here. This is just like the cartoon before, but it's now real data. We have the quark contribution from experiment here in blue, the gluon contribution here in green from a theory calculation, and the combined total here in red. And what we see by doing this combination is actually that the pressure inside the proton is greater than the interior of a neutron star, so the densest known object in the universe other than a black hole, but also a few really interesting qualitative features that we'd like to understand. So we see that the gluon contributions here, the green line comes out much further than the blue line. So the gluons significantly extend the radial extent of the pressure distribution. So this gives us an interesting qualitative feature from combining theory and experiment of an aspect of proton structure that we're beginning to understand for the very first time. So this is sort of where some of this work is going, to try to understand both qualitatively and quantitatively some of these aspects of proton structure and nuclear structure. So the pressure of the proton is an interesting and fundamental property in its own right that we might like to know about. But it leads almost directly to another question. Well, can we compute directly pressure distributions in nuclei? If we can, maybe that could be very valuable information. Maybe it can give us new information in our study of hyperon-nucleon interactions in the hope of constraining the equations of state of neutron stars. And so maybe there's a connection to be made there if we could do this sort of a calculation. In principle, we know how to compute the pressure distribution in nuclei from lattice QCD. You do exactly the same thing as for the proton, but for a nucleus. And in fact, we have some calculations in progress for some very light nuclei. But as I alluded to earlier, it's actually extremely computationally challenging. And it becomes more computationally challenging as you go to larger and larger states. So we're really limited by the available computing resources. So to give you a sense of this, there are really compounding factorial and exponential growths in cost as we go to larger and larger nuclei. And so at the moment, with current algorithms, current technology, current computer hardware, calculations are only just now becoming possible with controlled systematic uncertainties for light nuclei with atomic number, so the number of protons and neutrons, less than about 5. So very small nuclei. So to give you a sense of where these costs come from, so remember we're doing these integrals by sampling, right? And the noise, so the statistical uncertainty grows exponentially with the size of the system, with the number of nucleons. So you need to take exponentially more samples to get the same statistical quality result. But the amount of work you have to do on each sample, the complexity of the calculation also grows factorially. So that you have to contract all of the quarks together with each other in the nucleus, and that's a factorial growth problem. So we have a compounding exponential and factorial, which is why this gets so hard so quickly. Of course, there are many, many reasons we might be interested in larger nuclei, many of which I summarized right at the start. Intensity frontier searches for new physics, understanding the rest of the Big Bang nucleosynthesis pathway. And this is really what motivates our push for new algorithms that I'll come back to just in the last few minutes of the talk. But the program of exploiting what current resources we have for first principles QCD studies of nuclei is being pursued by a number of collaborations. You see the names and references to some of the collaborations here. I'm a member of the Nuclear Physics from Lattice QCD collaboration, which involves just a small handful of faculty, postdocs, and students across the world. And over the last decade, between all of the groups, there have been some really significant advances in this effort to study nuclei from QCD. So you see some of the highlights of our program in particular over the last few years on the slide here. Happy to talk about any of these in questions, but let me just mention a few recent studies in the theme of our talk today that are highlighted there. So firstly, one of the most straightforward questions we can frame when we're thinking about nuclear structure from the underlying quark and gluon degrees of freedom is how that structure is different from the structure of protons and neutrons. So how's that quark and gluon structure different in a nucleus from protons and neutrons themselves? So we encode these types of effects in what we call EMC type effects, named after the European Muon collaboration, who saw in 1983, as we see in this figure here, that deep inelastic scattering off a nucleus is not the same as deep inelastic scattering of the individual protons and neutrons. Deep inelastic scattering was the process we had before, firing the electron at the proton or the nucleus so hard that it breaks apart, right? And what we see here is the deep inelastic scattering cross-section ratio per nucleon for iron to deuterium. On the horizontal axis is the longitudinal momentum fraction carried by the struck quark. And we see that this thing here is not one, meaning that deep inelastic scattering of these nuclei doesn't look the same, right? So the question is, how do these EMC type effects, really nuclear effects, arise from the dynamics of the standard model? Can we compute them from first principles rather than from models? And so in very recent work, we've just made first inroads to this. So we've computed, going back to that simple static property that we talked about before, the breakdown of the momentum carried by different types or flavors of quarks. We were able to compute aspects of that in a nucleus, in this case, helium-3. So very small nucleus, three-body nucleus. So what you see in this figure is the ratio of the up minus down quark combination of momentum in the nucleus to that in the proton on this axis, and the up plus down quark combination of momentum in the nucleus to that in the proton. You see the blue ellipse, the constraints, these are the NNN PDF global fits of experimental lepton nuclear scattering data, so experimental constraints. And you see in red, the lattice QCD result from a direct first principles calculation. Now, there are significant systematics that had to be incorporated into this. Actually, the original lattice QCD result is between these gray bands. Then there had to be an extrapolation to the physical points, systematic uncertainties, which expand the error bar to the red. But despite those, what we see is that this constraint here from theory is more precise than that from experiment. Including it into the global fits to experimental data, you go from the blue ellipse to the purple here. And so we see an improvement, which is really the very first demonstration of the potential of lattice QCD on this front to add little pieces of information to global fits to experimental data to help reveal these EMC type effects, how nuclei are different from protons and neutrons in terms of their internal structure. Okay, so we can do a similar thing for other sorts of questions, in particular coming to some of these questions where we're looking for physics beyond the standard model, and we need to know some of the nuclear structure for the background and benchmarks in our searches. So it's the same sort of idea as what we just saw for the momentum fraction, but perhaps more exciting quantities that we could look at. So coming back to this question of dark matter that we came to very early in the talk as motivation. So of course, there's compelling evidence for dark matter, from rotation curves to galactic lensing, beautiful examples like this, the bullet cluster, where we're able to really see the difference between the visible matter, which is here false color in pink, and the matter that we can infer is there from its gravitational interactions through gravitational lensing here in blue. And we can understand that separation as clusters of galaxies collide and all of the visible matter collides and the dark matter passes right on through, which gives us a very visible separation between visible matter and dark matter in examples like this. This here is a picture of the Coma cluster, which was known as far back as the 1930s, when Fritz Zwicky saw that the gravitational mass needed to hold the galaxy cluster together is more than what you can infer is there from the luminous matter, from the stars that you see. So as far back as the 30s, there was an understanding that there's something interacting gravitationally that we can't see. So dark matter, right? Abundant evidence, gravitational evidence. We know that dark matter makes up about 5 times as much of this energy density pi in the universe as the normal matter, the standard model matter that all of the calculations I talked about studying. And other than knowing that it interacts gravitationally, which is how we know it's there, and it doesn't emit or absorb light, we really know very little about what dark matter actually is. It's one of the big mysteries of physics in our age. But we do have many, many theories, right? I really quite like this picture. Everything from theories with extra dimensions to supersymmetry to types of axions or axion-like particles, extra Higgs, all sorts of theories for what dark matter could be. And of course, what we want to do is constrain this space to rule out some of these possibilities and to support other hypotheses, hopefully. So how do we constrain that space of models for dark matter? So just one way is through direct detection experiments. So these fall into this class of intensity frontier experiments. These are searches here on Earth where we bury detectors deep underground to shield them and look for example, the weak interactions of a weakly interacting massive particle or a WIMP dark matter candidate with a nuclei in the detector. Okay, so these sorts of experiments can either see dark matter, or they can put constraints on the possible models of dark matter that are consistent with not seeing dark matter. Either way, what's needed to make those constraints is a translation from the observation of seeing dark matter scattering or not from a nucleus to the property that we want to know about, which is how strongly dark matter interacts with a single proton or neutron. And if we look at this figure here, which might be familiar, so this is limits on WIMP nucleon interactions from dark matter direct detection experiments. On the horizontal axis, we have the mass of our dark matter, our weakly interacting massive particle dark matter candidate. And on the vertical axis, we have the interaction cross-section for the spin-independent interaction of one of these WIMP dark matter candidates with a nucleon. And you see the lines here from different experiments, and that the space above these curves is ruled out by not having seen dark matter. And what you'll notice is that in making this plot, in putting these constraints on the figure, there's been a translation. So this experiment here used xenon as the nuclei in the detector. That's a very large nucleus, 130, 140 protons and neutrons. And yet the constraint being drawn here is on how strongly dark matter interacts with a nucleon that's a proton or neutron. So there's been a translation which involves nuclear physics. So the simplest approach to translating from not seeing dark matter scatter on a nucleus to the cross-section for interaction with a proton or neutron is through the Born approximation. That's to assume that the interaction is with a single nucleon in the nucleus at a time. And so then the cross-section just looks like this. It's the number of protons and neutrons times the matrix element for interaction with a single proton or neutron at a time. And this thing here, well, that is a single hadron matrix element. Like I said, we're in a precision era for single hadron matrix elements from lattice QCD. For whatever your model of dark matter is, we can compute this thing here with high precision. And then you can make the translation between dark matter scattering on a nucleus to a nucleon by scaling by this factor of A. But what if that's not a good approximation? What if dark matter interacts with multiple protons or neutrons in a nucleus at a time? So the cross-section could depend on multi-body physics, on nuclear physics. And then what we really need to know are the relevant nuclear matrix elements, not just the nucleon matrix elements, for the interaction of interest, which depends on the model of dark matter you're interested in. So then what we need is something like this, not just the interaction of dark matter with a single proton or neutron, but the interaction with 2 or 3 or 4, or with the whole nucleus at a time. So absent being able to reverse the search for dark matter into a measurement of some of these matrix elements, which of course we can't do, these actually can't be constrained for many dark matter models of interest by any experiment. And so the only way we can constrain them is through something like first principles lattice QCD calculations. So in particular, even though we don't know the actual form of dark matter, the low energy limit of a generic spin-independent interaction is scalar. And so if we have a spin-independent interaction of dark matter, what's relevant are the scalar matrix elements. And so those are those matrix elements that appeared in the previous slide. So that's what I'm showing here. This is from a lattice QCD calculation with a much larger than physical value of the pi mass. So systematics are not controlled here. but it was, this is the state of the art that we can do with available computing. And what you see in this figure is the deviation from that Born approximation, from the naive scaling for different nuclei. We have here 2-body nuclei, deuteron and diproton, and 3-body, helium-3. And in the different columns, you see different combinations of quark flavors, up minus down combination, up plus down plus strange, and so on. And it depends how dark matter actually interacts, what it is, which of these is relevant. But what you see here is as much as 10% deviations from the naive scaling in just a 3-body nucleus, just helium-3. But then the experiments are using much, much larger nuclei. And so the question is, if we have already unexpectedly large multi-body effects in very small nuclei, how can we constrain those in the very large nuclei used in these direct detection experiments? And just for context on why I'm saying unexpectedly large effects at 10% level, there are other matrix elements that you can measure in lots of different nuclei. So for example, axial matrix elements you can compute. And the deviation from the naive scaling is a fraction of a percent in helium-3, but it grows to tens of percent in larger nuclei. And here we already have tens of percent deviation in helium-3. And the question is, well, what about large nuclei? So like I said, there are still systematic uncertainties that need to be controlled. Most experiments use much larger nuclei than helium. We don't have complete systematic control of our calculation even for helium. But what this is a very strong warning that there are potentially unexpectedly large multi-body effects which shouldn't be neglected in the interpretation of dark matter direct detection experiments. And to me, what this emphasizes is that theory really still has an important role to play in this arena of interpreting the results of our experiments searching for dark matter, or in general, in interpreting the results of intensity frontier experiments. So we see the synergy between theory and experiment and points to a clear need for advances in computation to enable further lattice QCD calculations for these sorts of problems. Okay, so clearly we'd like to get our systematics under better control. We'd like to study larger nuclei. And there's a few ways of getting from small nuclei to large nuclei. And the first, which you think of immediately, is to interface and couple with ab initio many-body methods, where the protons and neutrons, instead of the quarks and gluons, are the fundamental degrees of freedom. And you have an intuition that this should work well, because of course we know that protons and neutrons bound together is a pretty good model for a nucleus, right? And so we have a nuclear effective theory where it's really the 1-body currents are dominant, the 2-body currents are sub-leading but non-negligible. I said 10% was unexpectedly large. It's still only 10%. So there is a hierarchy that 1-body is most important, 2-body less so, and so on. And so the idea is to match to these sorts of effective theory and many-body methods to extend lattice results to make predictions for larger nuclei. And through this path over the next decades, there's really great potential to connect from the standard model to some of these fundamental questions, both for problems like this, but for fundamental questions about the emergence of nuclear complexity, to really ground nuclear physics in the standard model by matching to lattice calculations where they can be done. But of course, there's still the question of what we could learn if we could push past the computational limits to go a little bit larger than helium-4 directly. And so just for context again, of course, many of the most interesting questions from a phenomenological perspective, just again, sticking with the intensity frontier theme, involve nuclei with tens of nucleons. So we'd like scalar matrix elements in xenon, A equals 131. To know whether neutrinos are Majorana particles or not, we'd like to be able to calculate double beta decay matrix elements to say, what nuclei you should use in your experiments to get the tightest constraints. Well, the lightest nucleus that undergoes double beta decay is calcium, that's A equals 48. There's a multi-billion-dollar experiment, June, a long baseline neutrino experiment being built in the United States to measure the neutrino mixing parameters and the mass hierarchy more precisely. They're doing neutrino scattering from argon, that's A equals 40. And again, to really convert what you see from neutrino scattering on argon to what you want, the neutrino mixing parameters, you need to do a translation, which involves knowing the axial form factors of argon. So lots of places where we really need better control of nuclear physics. So doing anything, we're not going to get to A equals 131, but even going a little bit larger to shore up this pathway of matching to many body methods, we'd like to do controlled calculations of even slightly larger nuclei. And these are exponentially and factorially harder problems. So ideally, we need exponentially and factorially improved algorithms to make that feasible with current computing. So just for the last few minutes, I want to give you a hint of some of the ways in which advances in computing and algorithms can feed back into these sorts of lattice QCD calculations. Okay, so numerically, what we're doing in these calculations is very high dimensional integrals. And I said we're doing them by importance sampling. So you're sampling the most important contributions more and the less important contributions less. So what that leaves you at the very first step of these calculations is a sampling problem. You need to sample these configurations, phi, with the right probability distribution. You want the important ones more and the less important ones less. And that probability distribution is given by the exponential of the action, where the action is, of course, the function describing the dynamics of the theory. So at its mathematical computational base, this is just a sampling problem. How do we generate this set of samples following the right probability distribution? The way we do this traditionally is through Hamiltonian or hybrid Monte Carlo, which you can think of as being a coupled position and momentum walk through Hamiltonian dynamics to explore this space so that you efficiently sample from the right probability distribution. So what you're doing in practice is updating from one configuration to the next via molecular dynamics, so you can simultaneously explore the level sets in probability density space and jump to nearby level sets by sampling in a way that preserves the distribution. Now, the problem with a method like this, where you're updating from one to sample to the next through some small change, is that there are correlations between the samples in your chain. And you might need to make some number of updates before you have a completely decorrelated sample. And in fact, because the updates are close to local or diffusive, so you can think about the changes propagating out like this. As the lattice spacing becomes small, the number of updates you need to change physics on some fixed physical scale, say the size of the proton, becomes large. If it's a very coarse spacing, maybe you only need to make a couple of steps before physics is decorrelated on this scale. If the spacing is very fine, you need to make many, many steps before physics is decorrelated on this scale. Of course, making many steps is expensive. So the cost grows of generating your decorrelated samples. And so this is a manifestation of critical slowing down in this context. And it's a really significant barrier for these first principles calculations. So let's think about this sampling problem and let's visualize it in this specific way where there's a clear implication here. What we really want to do is we want to sample these field configurations, which we're going to visualize like this. This is for, not for QCD, but for a scalar field theory where each site has just a real number. You can actually visualize the samples a lot like this. We want to generate these samples here with high probability. You can see they have sort of correlations on a characteristic scale compared to this, which is just random noise. These probabilities are actually genuine probabilities for a toy theory here. This is just random noise. This is very, very unlikely. These samples here with these sorts of characteristic correlation scales, they're very likely. We want to sample these much more than we want to sample that. That's fundamentally the problem. You see immediately a very clear parallel when we phrase it like this to a problem that's received a lot of attention in the machine learning community. That's the image generation problem. If you can design a machine learning algorithm to generate pictures like this, so these are not photos, they're fake pictures of faces. You can go to thispersondoesnotexist.com and refresh, and you'll get a new fake person every time you hit the refresh button. But if you can design that sort of a machine learning algorithm to give you this and not this, maybe you can do the same thing to give you samples like this and not this efficiently. So there's a very clear parallel. There's also a very, very clear and immediate difference that you can see already from this slide. If we're generating pictures of people's faces, we never want this. This doesn't look like a face at all. This is also random noise, but we do want it just very, very rarely. And we want it with precisely the right probability. So if we stack up and really make this comparison between a set or an ensemble of lattice QCD gauge fields that we want, and between a benchmark image set used for machine learning, we see these differences here. So first, the one that we've already mentioned, it's really only the set, the ensemble of these gauge fields that has any meaning. We want that to obey a precise probability distribution, as opposed to pictures of faces, where each picture is a good picture of a face or not on its own. Then we also have actually an extreme inversion of the typical data hierarchy. So each image in this benchmark set is described by something like 3,000 numbers, but there are 60,000 samples available to train your machine learning algorithm on. We have each image described by 10 to the 9 to 10 to the 12 numbers, but we only have or want, order thousands of samples. And if we had them, then we wouldn't need to be generating them. So there's a really extreme inversion here of this ratio of numbers. So anything that involves training data isn't going to work. If we had that data, we'd have the samples we want. Long distance correlations are important and encode the physics. In a picture, often local structures are important. Things like a nose or an eye sort of has a local structure, and things like convolutional neural networks are specifically designed to work well for images. We have physics symmetries inside our theory, which you don't have in images. So we have rotations and translations with periodic boundary conditions as field configurations. These are the same. There's just been a translation and a rotation, and they should have exactly the same probability of happening as images. They look quite different. Even more for QCD, we have internal symmetries, gauge symmetries. We actually have, instead of a number at each site, an SU3 matrix on each link of this lattice. So 3 by 3 matrices with unit determinant. And gauge transformations transform all of those links differently, but in a correlated way across the whole configuration. So trying to visualize as images, these things would be identical from our physics perspective, and should have exactly the same probability. But of course, these sorts of symmetries don't exist for images. So it becomes clear very quickly that although there's a very clear parallel, we also can't just take any sort of machine learning algorithm designed for other problems and apply it to these sorts of physics problems. We really need to design custom machine learning for physics from the ground up. And I'm advertising here, we've just launched a new institute in the Boston area called IFI, the Institute for Artificial Intelligence and Fundamental Interactions. And the whole purpose of our institute is to bring physics and AI together to develop what we're calling ab initio AI. So provably exact physics, our AI algorithms with the physics built in from the ground up. Okay, so just for the last 2 minutes, I want to give you just one hint of an approach to this generation problem using AI, using what are known as flow models. And the idea is very simply just a change of variables. If you have a map that takes you from an easy to sample distribution, think about drawing, say, uniform random numbers or Gaussian, something like that, from an easy to sample distribution to the distribution you actually want. And moreover, if that map is invertible and with a tractable Jacobian, then you're done. You take samples from the easy distribution, you put them through your map, out come samples from the hard distribution. And the invertibility and the tractable Jacobian means that even if this map isn't quite exact, you can correct for the errors through a known algorithm, Metropolis, Hastings, accept, reject step. So then you've changed your sampling problem into learning the map and sampling from a trivial distribution. So we can build this sort of a map while maintaining all of the features we need. So the invertibility, the tractable Jacobian that's needed to make sure this is one-to-one and you guarantee correct sampling in the limit of a large number of samples. We want to build in all of the symmetries by constructing a complicated function as the composition of many simple layers with specific features. We can even bake in, we can develop these layers to bake in exactly the symmetries of our theory, which is a lot easier said than done. But then the machine learning part of this is just optimizing all of the free parameters of this very complicated function to give us the closest approximation of this map, this trivializing map, if you like, between the easy distribution and the hard distribution that we really want samples from. So just some hints of the challenges that arise here. So the field configurations that we actually want are actually represented by each link of the lattice having an SU3 matrix, so a 3 by 3 complex matrix with unit determinant on them. And so we have group valued fields. They don't live on the real line, but on compact connected manifolds. So first you have to go back and say, well, what if I want to do machine learning, not on real numbers, but on compact connected manifolds, and design that and make sure you don't have any numerical instabilities, discontinuities. How do you even design this sort of algorithm, even just on variables on a circle? And then build in all of the symmetries of the theory. And I'm not going to tell you how we do this, but I can point you to some references, and I'll give you a sort of artist's visualization of how you can take in information from one layer to the next in this sort of a model and pass it through with all the symmetries incorporated. And I'll also give you an example of the impact. So this figure here shows the cost of generating field theory samples using conventional approaches and using this sort of an AI algorithm that we've developed for a toy model of a U1 field theory. The only reason I'm showing U1 here and not SU3 is that there's a nice topological freezing problem. There's a nice slowing down in U1 in just 2 dimensions. For SU3, you have to go to more dimensions to really see it so clearly. And what you see here is the cost. And here we're changing the parameters of the theory from left to right, moving along a critical line where conventional algorithms get more expensive, where you need to make more updates to generate independent samples. And you can see here in blue and in gray, conventional algorithms, indeed, going from left to right, the cost goes up. The machine learning algorithm remains fairly flat, moving from left to right, it goes up a little bit. That's because it gets harder to train and optimize. But over here on this side, you see orders of magnitude more efficient sampling than conventional sampling approaches using these sorts of tools. So it's really a proof of principle success. It needs to be scaled up to impact the sorts of first principles calculations I've been talking about. Whether or not that can happen is still an open question. But the idea I want to leave you with is that it's just the very beginning of this field, of this sort of ab initio AI, of building in fundamental physics principles right into AI architectures. But it's already clear that there's huge potential in this context of understanding the structure of matter from first principles theory calculations. And we've only just begun the development of this exciting new field. And I look forward to seeing whether it can have impact on nuclear theory. So just to close, so there's still a way to go before we make real impact on our applications. But it turns out thinking about some of these things is also useful in other contexts. So developing flows on compact connected manifolds. Well, the joints of a robot arm, the positions of those joints are described by variables on circles. And so once you've developed these sorts of machine learning tools that work on variables on circles, there's immediate applications to robotics. At a similar time to our work, similar ideas were developed in the context of molecular genetics and drug design. So there's sort of great potential, and it's not clear yet exactly where the bulk of that potential is going to land, but lots of potential in these sorts of tools. Okay, so let me just finish with a reminder of the story that we've seen. So first principles calculations of the strong interaction in the standard model are revealing proton and nuclear structure in new ways. So from basic details of the proton's internal dynamics that we're understanding for the first time, in some cases by combining theory and experiment. So I gave a particular example of the pressure distribution, through to very early first principles calculations of nuclear effects in the platonic structure of nuclei. And so input for theory searches for physics beyond the standard model. In particular, constraints on the nuclear effects needed to interpret the results of intensity frontier searches for new physics. And then as we continue to push the physics frontier, there's a new generation of provably exact, physics-informed machine learning algorithms that's promising to open up calculations that were previously computationally intractable. And so it's clear that there will be lots of interesting developments over the next decade or so as we continue to push this further to understand nuclear physics from the most basic building blocks. Thank you.
That's super. Thank you so much, Phiala, for such a wide-ranging, really interesting talk. So if you have time for a couple of questions, I'm sure there are some questions. So people can, if they'd like to raise their hand, or, oh, Nigel's already raising his actual hand. I was thinking a Zoom hand, but there you go, Nigel. Go ahead, please. Oh, you're muted now again, Nigel.
Okay.
Yep, perfect. Yep.
Very nice talk. Just wondering if this shows a light on the proton radius problem.
Yeah, so you can compute the proton charge radius from lattice QCD, but the precision is really not quite good enough to distinguish between the different measurements from electronic and muonic hydrogen experimentally. So there's lots of effort in this direction, though. The work I'm talking about doesn't shed light on that problem, but there are others working very hard on that. And in principle, certainly, you could just compute the charge radius from lattice QCD. It's a matter of getting the precision and the control enough to distinguish.
Are there other questions? So now I've lost, hang on, I just don't see the hands. So I don't see anybody asking a question just at the moment, so I'm going to jump in because I have loads of questions actually, but I'll start with one quick one that, just because I don't really understand very much about these machine learning algorithms that you talked about, but
Yeah.
you did mention the autocorrelations and the role of correlations in importance sampling. So what happens in these generative flow algorithms to autocorrelations? I mean, my naive question is, do they get better or worse, or maybe that's the wrong question?
Well, I mean, to first order, there are none, because you're just taking samples from, completely independent samples from the easy distribution, putting them through an outcome samples from the distribution you want. So there's no sense in which you're updating from one configuration to the next at all. So you do end up getting
you really decoupled that idea of an update algorithm.
Exactly, there's no update. So the only way you get autocorrelations is because the map isn't perfect. You're not sampling from exactly the right distribution, so you need to correct it. And one way of doing that is to compose your completely independent samples in a chain and do an accept reject step. And then if you reject, obviously there's a correlation. And so you get autocorrelations if you make a lot of rejections. But the samples are still completely independent. So it depends on, you can get autocorrelations from that correction step if your model is not perfect, which of course it never is.
Yes, okay, I see. Oh, that's okay. Yeah, that's interesting. So this you've tried for this U1 model, and is that it so far, or where else have you?
We've done U1, SUN, actually up to SU100. We've done the pure gauge, we've done plus fermions in the Phiala model, and we have a paper coming out hopefully this year on the Schwinger model, so combining fermions and gauge. And we've also done very tiny tests on QCD that we're still working on. Scaling is going to be hard.
That was my next question.
It's mostly the engineering problem of scaling, because we would need to have machine learning models that are the same scale as the biggest ones used in industry applications. Think about things like, AlphaGo, ImageNet, these sorts of things. We'd need to, and all the engineering that goes into running a machine learning model that big, we would need to be running big machine learning models, and whether you can do that, with academic resources.
Well, I guess Aurora, that's what you're waiting for, I guess.
Exactly. We have a project on Aurora actually to scale this up.
So are there questions? Other questions?
Yes, I have one.
Oh.
Hi.
Yes. Hi, Patrick. Sorry, I didn't see you. Yes, go ahead, please.
Hi, no problem. Thanks, Phiala, for the nice talk. You mentioned explicitly for one of the models that you simulated or trained that you have periodic boundary conditions in the first place. So if I think about the standard QCD algorithms we are using nowadays, I imagine that all these kind of distributions that you want to sample in the first place depend a lot on not just the bare parameters, but also the topology, so the boundary conditions that you apply. So you would have to, I guess you would have to train your algorithm for different boundary conditions in the first place. If you don't do it in some kind of master feed way on a very large lattices where the boundaries don't really matter in the end. Can you maybe comment on that?
Yeah, so essentially, the configurations you're generating are going to be exactly the same type of configurations you'd get from HMC for whatever action you want. So what we have primarily been focusing on is, Wilson-Clover gauge action. You've got anti-periodic boundary conditions for the fermions, and so you build all of that in. If you wanted to do a different action, you'd have to redesign the architecture to particularly suit that action. Yeah. So if you want to change the boundary conditions or any aspect of the action, the architectural choices that you'd make might not be the same. But ultimately, the samples themselves are just, they're just samples. It's just numbers stuck into the gauge field, which you can just put random numbers in. It will be a genuine gauge field configuration. The problem's getting high quality enough samples. So actually, I should say you don't even need to build in any sorts of symmetries to make guarantees of exactness at all, in fact. The fact that you have a one-to-one mapping of these distributions, that every sample is guaranteed to appear, and that you have an accept-reject step, guarantees that even if you don't bake any symmetries in, you'll have in the limit of a large number of samples the right distribution. The only question is, can you optimize that map when you have such high dimensional symmetry groups that you're trying to approximate with various degrees of freedom in your distribution? And can you get a high enough quality model so that that limit of large number of samples is actually something achievable in approximation in a short time? So in some sense, the first answer to your question is you don't need to worry about it, but the practical answer is yes, you have to design everything with your action and boundary conditions in mind.
Okay, thanks.
Are there other questions? I'll ask maybe one more then. Oh, Nigel. Yes, sorry, Nigel, go ahead.
Mute again. I'm
Yeah.
just wondering if the deuteron is as easy to study as the helium, as helium-3.
Well, when you go to large values of the pion mass, where in our current calculations, it appears to be more deeply bound than in nature, it's easier to study than helium-3 because it's slightly smaller. When you get closer to the physical pion mass, when you have a very small binding, it gets tricky.
Sure, thanks.
When you did that calculation, you showed us results, Phiala, for in the dark matter applications for the matrix elements where you have this unexpectedly large deviation from the expected scaling or the naive scaling, what I'm not sure what you called it. But is there any understanding of how that might scale with the pion mass? Because this was a fairly heavy pion mass, is that right?
It's a very heavy pion mass. So we have calculations at about half that pion mass, which is still very large, 400 MeV,
Yeah.
and it seems to be similar, but the uncertainties are a lot larger. So at the moment, we're working on reducing them, of course. So, but there's no real theory expectation for how that should scale.
Right, that's
really.
what I was wondering, or some sort of phenomenological model that you could understand quark mass dependence, pion mass dependence.
I mean, since they're much larger than you would expect from those models, I'm not sure how you trust the.
Yeah, okay, that's a good point. Yeah, okay. Okay, so I don't see questions, and I'm also a little bit conscious that Phiala does have to teach. So
Yeah, I have 12 minutes.
So I know, but I'm sure you'd still like some time to just catch your breath. And so I think unless there are any urgent questions, I would just like to say thank you very much. We really very much appreciated such a really interesting talk. And I guess one of the unintended or unexpected advantages of this pandemic has been that we can invite people like you to visit us virtually and to give such nice talks. So it's been really great. And when all of this insanity clears, then we're looking forward to welcoming you to Dublin in real life.
Thank you very much.
Yeah.
It was a pleasure.
Yeah. Thanks, Phiala. Thanks so much.
Thank you.
Okay.
Bye-bye.
Thanks, everybody.
Thank you. Bye-bye.
Thanks, Anna.
Thank you. Thank you. Thank you, Sinead.
All right. Talk to you soon. Thanks, Marius. Bye.
Bye.